around. Now, when we're talking about motors, we just need to talk about losses. You put stuff in, you put power in, and you get power out. And there's a difference between the two. The differences between those two are caused by things like copper losses. Copper losses means there's resistances in the coils. Iron losses. Iron losses tend to be due to eddy currents. That's Mrs. Current's son, Eddie. Fan losses, there's a fan on there, and friction losses. That's the way of saying the other bits we don't know what they are. So there's a difference between what goes in and what comes out. Proportionally, these differences are shared amongst the rotor and the stator. As you can see, the iron losses are very big in the stator. That's because there's a lot of iron work there. Now, we have some problems with reducing the speed of a motor. One of the main problems we have with reducing the speed of a motor is that it overheats. It gets hot. Probably, if nothing more, it's because of the fact that the little fan on the back isn't running as fast. So if you reduce the speed of a motor, it tends to get hot. Our classic solution for this used to be to buy a bigger motor. If you bought a bigger motor, then you had a larger surface area, you had larger coils, and it didn't get so hot. Now, you tended to run into some problems here. You've only just talked the accountant into letting you buy a VSD, and now you've got to go back to him and say, actually, yeah, I've got to buy a motor nearly twice the size. So that's a bit of a downer on it. All of our problems come from, the root cause of our problems is things called harmonics. VSDs produce harmonics like they're going out of fashion. The reason VSDs produce so many harmonics is because, in actual fact, the frequency isn't running around the 50 hertz mark. It's actually producing these radio frequencies at the 10 kilohertz is. And those radio frequencies are going to produce lots of harmonics. Harmonics means heat. Harmonics means the damn thing tends to overheat the motor. Put simply, you put energy in and you get energy out. If there's any difference between the two, that's going to come out as heat. And what's been found is that as you reduce the frequency, there's bigger and bigger difference between the energy you put in and the energy you get out. The torque is reduced, so the heat increases, because that energy has to go somewhere. So, there's solutions to this. One solution is to install filters, passive filters in the VSD. Now that would make the VSD more expensive. It would also restrict how quickly we can change the frequency, because it's a filter. Filters restrict how quickly you can change things. Another thing which apparently helps is using different VSDs. So you'd use one VSD to do one frequency range and another VSD to do another frequency range. Now, that's what they used to do 20 years ago. They don't do that anymore because it's ridiculously expensive. The third method, pulse width modulation, we're going to come back to in a moment. Sorry, space vector modulation. I'm going to come back to that one. Another way that would make it even better is if we could up the frequency to, say, 1,000 kilohertz. Now, if we do this, we're going to be outputting in, the microwave frequencies. That's not going to be very healthy for anybody. So what we're going to look at, one way we're going to look at, is a system which is called space vector modulation. Company WEG, the Brazilian firm, they call it space vector modulation. Other firms call it different things, but most VSDs have the ability to do this space vector modulation. So, going back a step then, we have a problem that if we reduce the speed of the motor, we increase the heat. In fact, if you take a normal pulse width modulated motor and you run it less than 15 hertz, then what's going to happen is it's going to change color. All the paint will come off and it'll smell funny. because you're going to cook it. Ways of fixing this, and yes, you've come up with one of the solutions. The way we fix this, use a bigger motor, bigger coils. The other way is bolt a big fan on it. What you do is you have an external motor driving a fan which force cools it. That's a big solution. A lot of people do this. The third solution is what's called space vector modulation. And before we get into too much details of water cooling and other cooling, if we just look at space vector modulation, you'll see how that works. Now, to understand this space vector modulation, you have to understand that there are ion losses in a system. These are losses which are caused by eddy currents. Eddy currents is a very, very naughty boy. He comes out and he runs round and round in circles. And if he runs round and round in circles, he uses up lots of energy. So we need to stop him running around in very big circles. The size and the shape of the circles that eddy currents runs round in varies with things like the frequency of the AC that's causing this. Problem we have is we put, let's get a decent pen. We put power in to a motor, we get power out, and anything that's different between the two is basically heat. What we found is that as we reduce the speed of the motor, there's a bigger difference between the power in and power out, and there's more heat coming out. Now, what's causing this is that we are over-magnetizing the motor. We're putting too many volts in, or we're not putting enough volts in. We're putting the wrong volts in for the frequency. The equation that we use is that torque is a constant times the voltage divided by the frequency, where K is a constant for the motor. Actually, it should be KF, because it's K for a particular frequency. So at any particular frequency, an individual motor responds differently. But we do have this equation which says that torque is a constant equals a constant times the voltage divided by the frequency. The problem what we've been doing is we've been altering the frequency, but we haven't been altering the voltage to suit. So we've ended up putting too much magnetism into the motor. We over-magnetize it. And when you put too much energy in, you just waste that energy. And all that wasted energy comes out as excessive heat. The way to fix this is to change the voltage at the same time as we change the frequency. Now, at the top here is a standard phasor diagram. I don't know about you, but when I was at TAFE, I hated these diagrams. This is a standard phasor diagram showing three-phase electricity and showing three phases at three different times. And at all three different times, the center voltage, the center of the Y, is at 0 volts. When you add the vectors for all three phases, we always get 0 volts as the common mode voltage. So at any particular time, the 0 volts, the neutral is at 0 on three-phase motor. That's pretty well what we'd expect with a modern three-phase motor. In the olden days when they used to hand wind them, you used to get some neutral currents. But nowadays we don't expect that. We expect 0 volts on the neutral. Okay. What we do is we change the voltage to suit the frequency. So that as we change the frequency, we also change the voltage. That way the voltage and the frequency match, and we don't get the over-magnetization. If we don't get the over-magnetization, we don't waste energy. So we change the voltage. The way we change the voltage is by stretching the waveform. So we stretch the waveform at the top end, or if we want to reduce the voltage, we squash the waveform up at the top end. So because we're able to create basically whatever wave we want, we can change it from a sine wave to a slightly stretched out sine wave. And when we change it from a sine wave to a stretched out sine wave, the RMS value, this is the RMS value here, the RMS value, the root mean square voltage value, goes up and comes down. The one slight downfall of this is that now the center point is occasionally not at 0 volts. If we take time 2, which is this line here, at this point here, time 2, the center point of the three phases is not 0 volts. What's happening is we've got a slight neutral voltage, 2 or 3 volts. Whatever you get in the coil, of course, you also get in the rotor. So now we've got a slight voltage, center point voltage in the rotor. It's called a common mode voltage. What we've got is a very slight common mode voltage inside the rotor. Now, you wouldn't think that's too much of a problem, except for now we have the rotor inside an AC motor. The rotor is at a slight voltage above Earth. When you have a slight voltage above Earth, where does it want to get to? Yep, it wants to get to Earth. How is it going to get to Earth? What's its route to Earth going to be? Through the bearings. A little bit of an oops then. Here's the problem we have. We're going to crater the bearings. We're going to completely mess the bearings up because of the common mode voltage. Not so good. Any idea how we're going to fix this problem? We could use insulated bearings, but it's still going to find its way back somehow. It's going to find its way to Earth. I'm not sure I know what you mean, Des. Yeah, I'm not going to use a wound rotor. I've just got your standard squirrel cage rotor. Okay, I'll tell you. Slip rings and brushes. Insulated bearings, slip rings and brushes. Something to bear in mind. If you're working on a motor that's running off of a VSD with space vector modulation, it may well have insulated bearings and slip rings and brushes. If this is the case, when the motor goes off and gets the bearings changed by the fitters, make sure it comes back with insulated bearings on one side and not insulated bearings on the other, and make sure that the brushes get put back onto the shaft. Of course, it's one more thing to go wrong now. And the reason we didn't use one of the reasons we didn't use DC motors in the first place was because we didn't want slip rings and brushes, but there you go. So, that's one way of stopping a motor overheating, using space vector modulation. According to the manufacturer's literature, and I've got reason to believe this, according to the manufacturer's literature, with space vector modulation, you can start a motor up and run a motor all day at 1 hertz full torque. So with space vector modulation, you're able to run at whatever speed you want, full torque, with no overheat. Now, somebody did come to see me last week. They did the course the week before, and they went out and they looked at their VSDs, and all of their motors had been running extremely hot. And when they first installed them, the motors were running extremely hot, and they kept tripping out the VSD on overheat. So what they did is they went in, of course, and they changed the overheat limit. What these people did last week, the people that were in the week before last, sorry, is they went back to their site and they looked at the VSD documentation, and they found the manufacturer's equivalent of space vector modulation. I think it was called voltage modulation or something along those lines. They enabled voltage modulation, and immediately the temperature of all of the motors dropped 20% of what it was running before. So it does work. They told me they then phoned up the VSD's rep and told him what they'd done, and the rep had got no idea that you could even do it. So that's something to be aware of. But this really, really does work. If you use this space vector modulation or voltage modulation or whatever it is called for your manufacturer, then you will drop the temperature of the VSD motor, and you'll be able to run it less than 15 hertz. And because you're not putting the extra energy in, you're not getting the extra heat out. It doesn't affect the speed control in any way. The VSD works completely normally. The only thing that you do have to do is that each motor has got its own iron loss or iron constant fingerprint, if you will. And that is an individual thing for each motor. So when you buy this, you generally buy the VSD and the motor as a matched pair. And they come as a matched pair, with the VSD knows all of the motor's iron loss characteristics. If you ever have to replace the motor with another motor, then what you have to do is you have to wire it all up, and then you have to put the VSD into a learning mode. I think in a lot of cases it's only a case of pressing a couple of buttons and waiting half an hour. And then what the VSD does is it winds the motor up and down for half an hour or so. And, oh yeah, okay, it's called a magnetization, is it, on your one-stroy? Well, basically the VSD goes off and learns how the motor works, and it learns that motor's magnetic fingerprint. And so this system, called different things by different manufacturers, but effectively what we're doing is we're changing the voltage to change the magnetization so that we don't over-magnetize. If we make sure that we don't over-magnetize, then we don't overheat, because we don't put the extra energy in the first place.